make it small, I don't need to make the external force 0. If the time difference between the initial and final state I'm looking at is very small, then the impulse that the force creates will be small, even if the force itself is non-zero. To change momentum, you need to give the force some time to change momentum. So if everything happens in a short time instant, just really fast, then the force will not have enough time to change the momentum, and we can still use momentum conservation in that situation. So an example is fireworks. When you look at fireworks, it usually goes outward. You seldom see a firework that just go all the way in one direction. It is because the firework explodes at the highest point. So when the firework flies up with projectile motion and reaches the highest point, its velocity is 0, the momentum is 0, so our initial momentum is 0. However, gravity is always there during projectile motion. It's always non-zero going down. But if the explosion of firework happens fast enough, then the time difference between initial state and final state will be really small. And the impulse caused by gravity will be too small, and we can neglect it and say the momentum is approximately conserved. The change of momentum in initial and final state is basically 0 because gravity don't have enough time to change the momentum. Okay? So if initial momentum is 0, then the particles in the final state must fly in every direction. So the total momentum in the final state will sum up to 0. We can see this one kind of cancels this one, and this one kind of cancels this one. So that's why you see the firework will explode like in all directions in the sky. Okay? So that's how we can use momentum conservation even though the external force is non-zero, as long as it happens. Water. Alright, let's go a little bit detour back to energy. So here you see that I only look at external momentum because we say I only look at external impulse because the internal force will just cancel. It's not what happened for energy conservation because when we change energy, we are looking at the work done on all the particles. Now, work is not force times time. Work is force relative to the displacement of that particle. When you look at the work done on the second particle, you need to dial it to the work to the displacement of the second particle. And for the nth particle, the work done on the nth particle is a force on it relative to the nth particle's displacement. Now, for the particles in a system, does all the particles have the same displacement? No, right? It's not like time difference. For impulse, the time difference is the same. So the internal force will cancel, and the impulse caused by internal force will sum out to 0. But here, the internal work done by the internal forces will not cancel because they are adapted to different displacement. You need to adapt them to the displacement of individual particles. So this is why this is non-zero, because you can't just take displacement out of the parentheses. These displacements are the displacement of the individual particles. It's not going to be the same for all of them. That's why we have this term as the change of internal potential energy with a minus sign. And that is very important because when you are doing agricultural activity, what you essentially is doing is to change the energy of the sunlight into the internal potential energy of the plants. And then you can eat the plants and turn that internal potential energy into your body's energy. Any question with that? That should be important for you guys. So let's go back to momentum conservation with one more example. When the time difference between two states is small, the momentum is approximately conserved because the external force don't have enough time to change the momentum. What I'm going to demonstrate next is called hand hops. What I will do is to put my hand on the ground and try to hop. But when I'm going to hop, I will keep my hand straight. What I'm going to do is to use momentum conservation to hop up. You will see me curving my leg like this and keeping my hand straight. This is my head. This is my eye, nose. Okay? So to do hand hops, I will kick my leg. Upwards. So when my leg is going upward, it has velocity, and my leg has mass. So it will have a momentum. Okay? But when I kick my leg to the very end, my leg cannot extend further. I mean, that's how my joint works. It can only go that far. So when I kick all the way up here, my leg cannot extend more. But momentum is conserved. My leg already has momentum when it is moving up. This momentum cannot be destroyed. It must go somewhere. So what will happen is that this momentum turns into the momentum of my entire body. My entire body will move up with the same amount of momentum. And during the time, or during the process of momentum transition, during the time it takes for the momentum of my leg to go into my body is very short. So even there's like gravity, normal force acting on my body, the momentum between this state and this state is basically conserved. So I can use momentum conservation to calculate the momentum of my body based on the momentum of my leg. So if my body has momentum going up, it has velocity going up, and then I can go up. Okay? Any question on how to do hand up? Alright, so pay attention to my legs. You will see my hand remain straight all the time, but I'm kicking my leg to do hand up. Alright? You guys see that? Do you need to see it again? Good. Alright, so that's how you do hand up. When you do hand up, you keep your hand straight because you're not hopping with your hand. You are using momentum conservation. Okay? So you will see that the height I jump up is pretty small. In your previous homework, you saw that the height you go up will be 2v squared over g, which v is the velocity of your body going up. You can solve by using energy conservation in your homework. You store it go upward with speed v, and then this is how high you can get. You can see that it only depends on the speed. So the reason I can only jump up this high is because my speed of the body is small. But why is it small? When I'm kicking my leg, I can easily make it fast. Like, I can easily kick my leg fast, as you can see how high my shoes go. So if my leg is having a big velocity, why does the velocity of my body become so small? This is because momentum is not velocity. Momentum is mass times velocity, which means that I need to consider the mass difference between my leg and my body. With momentum conservation, the initial momentum, which is the momentum of my leg, equals the momentum of my body. So P leg should equal to my body's momentum. But momentum is not velocity. It is mass times velocity. Let's say my leg has mass small m, and my entire body has mass big M. When I look at the momentum of my leg, it is going to be the mass of my leg times the velocity of my leg.